Hello. So in this video, we're going to be talking about Haberman's section 3.6. And kind of the goal of this section is to describe and work with and kind of get a feel for the complex form of Fourier series. And so here, when we say complex, we mean in the sense of complex numbers. Okay. So in particular, our goal will be if we have a function f of x, okay, kind of the series that kind of we've already worked with and started understanding and playing around with, take the form, right, a0 plus the sum equals 1 up to infinity, a sub n cosine of n pi over Lx plus sum from n equals 1 up to infinity, b sub n sine of n pi over Lx. Okay. So one thing to notice is, right, we have a linear combination of cosine and sine. Okay. This piece right here, e to the I n pi over Lx, it's also a linear combination of cosine and sine, right? And this is via Euler's identity, where we write e to the I n pi over Lx. This is cosine n pi over Lx plus I sine n pi over Lx. Okay, so the fact there's some relationship between these cosine pieces and this complex exponential shouldn't come as too much of a surprise. Right, and again, that's through Euler's identity. But the question is, if we write kind of a series in this way, where we have this complex number and these possibly complex coefficients, do we end up with the same representation, same kind of object as writing out the cosine and sine pieces explicitly? Okay. So this is the goal of this video, right? Make this connection between these series of complex exponentials and kind of the series that we've already seen before. But before we go on, the question you might have is, well, why bother with this kind of other representation of functions, okay? Especially one that incorporates complex numbers, where the functions and the things that we care about, they're all real. So some answers to this are, well, in some sense, there's some nicer kind of theoretical properties. And by this, I mean, right, so the kind of real version of the Fourier series is going to be equivalent to the complex exponential version, right? So in a sense, they're the exact same object. So, right, maybe they'll have the same properties, okay? What I mean by this is more of, in many instances, it's easier to work with these complex exponentials than it is to work with sums and products of trig functions, okay? Yeah, and then as well, there's some identities that kind of pop out and are easier to see and interpret than they are if we just look at these cosine and sine terms. Okay. In addition, and you might say kind of along with, or similar to nicer theoretical properties, is that a lot of computations are actually easier, right? And so kind of as an example, if we write out the integral cosine, I'll write it as n theta, say cosine of m theta, d theta. And if I said evaluate this integral, right? If you don't remember, or if you don't have a lookup table for kind of this integral identity, right? This may be a hard integral to figure out. But if instead I say integrate e to the minus I m theta, e to the I n theta, d theta, well, in this case, what is this whole thing equal to? This is just the integral of e to the I n minus m theta, d theta, right? So this piece right here is just the integral of an exponential And so this integral is going to be 1 over I n minus m times e to the I n minus m theta, I guess, plus a constant or whatever. Okay. So already working with these complex exponentials, right, similar sort of kind of integral, computations become almost immediate. Okay. And finally, there are a lot of nice direct kind of applications to signal processing and a lot of very kind of applied things that if you just try to work in the real setting, become a lot harder to work with. Okay? And so one of these in particular is, we have formulas for, so up here. So for example, this coefficient a sub n, this was 1 over L integral from minus L to L of f of x cosine n pi over L x dx. Okay, so we have a formula we can write down, but if we want to compute these Fourier coefficients kind of numerically, especially if we're doing like live sound and we want to what are they called? Those meters that kind of like show the different frequencies of the sound waves as the sound is coming in. If we want to compute those frequencies and figure out what's in the sound quickly, right? Trying to compute these integrals is going to be incredibly tough, incredibly time and just general resource heavy. And so it's not feasible to get a lot of these coefficients just on the fly. If instead we work in this complex exponential framework, there turn out to be very fast and very good ways of getting these Fourier coefficients quickly and nicely, okay? Which lets you do a lot of the sound kind of visualization on the fly. Okay? Yeah, so there are a number of reasons why we would want to work with and kind of keep these complex exponential pieces in mind. Okay, so then the question is, well, how do these really relate? And so I gave some broad indication, right? Well, Euler's identity, this is a sum of that plus I times that. But that didn't really tell us anything about how this coefficient C sub n relates to A0, AN, and B sub n. Okay. So what we're going to do next is we're going to just see how this relates to each of these three coefficients. Okay. And so once we have a connection there, then we can go backwards and then we can see, well, if we have A0, AN, and B sub n, how do we construct these C sub n? Okay, and so that'll give us like a one-to-one connection between the complex form and the real form, and we'll be good to go. Okay, so kind of as above, right? Remember we have Euler's identity. So if we plug in e to the I minus n pi over Lx, what do we get? Well, we get this linear combination. Okay. So technically there's a minus sign here and there's a minus sign here, right? Just plug in directly here. Sine of minus whatever is equal to minus sine of whatever. Cosine of minus whatever is cosine of whatever. Okay, so we've already done that simplification. So what we're going to do is we're going to take this complex exponential series and we're just going to plug in this bit right here. Okay. So yes, this sign is negative. The sign that we wrote up here was positive. In practice, it doesn't really matter, in part because we're summing up from n equals negative infinity up to infinity. Okay. But anyways, what we're trying to do here is just get a relation between these C sub n and the other coefficients. Okay. So if we plug in this, if we plug in this for that, what do we get? we get this piece, right? Just distribute the C sub n. Okay, now what we're going to do is we're going to break up the sum into three pieces, right? The piece for n equals 0, the piece for n is positive, and then the piece for n is negative. Okay. So when n is equal to 0, we're going to get a C sub 0. This is going to be cosine of 0, which is 1. This is going to be sine of 0, which is 0. Okay. So when n is equal to 0, all we're left with is C sub 0. For the positive piece, well, we don't really need to do anything, right? Yeah, right. Just because kind of this is good as is, plug in n, it's positive, don't need to worry about the sign here, don't need to worry about the sign there. So this is all good to go. Now, if we look at the negative n, right, what we're going to do is we're going to write it in a way so that we're summing over n equals 1 up to infinity, positive. But we're going to incorporate the fact that we have a negative sign kind of in these actual arguments here. Okay. Yeah, but the point is, right, what we have up here is exactly the same as what we have down here. It's just splitting up these pieces and then being a little careful with the indexing for the negative things. Okay. So what we're going to do next, we're not going to change this. We're not going to change this. But we're going to pull the negatives out from here. Okay. So cosine of negative whatever is just cosine, right? So this is equal to that. Pull out this minus sign here. Sine of negative whatever is sine of whatever. So you have this. Okay. Cool. Our goal here, though, is to write this in terms of, right, try to match this with the real Fourier series. And so what we want to do is we want to pull out just the cosine pieces and then pull out just the sine pieces. Okay. But luckily, how we've been bookkeeping, we can do that almost immediately, right? These sums are over the same kind of indices. These cosine terms are going to match up. These sine terms are going to match up. And so then all we have to do is bookkeep what happens to these pieces. Okay. So C sub 0 isn't going to change. If we collect all the sine if we collect all the cosine terms, what we're going to end up with is C sub n cosine plus C sub minus n cosine. So that gives us C sub n plus C sub minus n times cosine of n pi over Lx. Now, if we do the same thing with the sine terms, what we're going to end up with is this expression, right? So it's a little more complicated, but that's okay. The I and the sine, these are common to each of these pieces. Okay. So if we pull those out, we're going to be left with C sub minus n minus C sub n. And that's exactly what we have here. Okay. Cool. So what we've done is we've taken this complex exponential sum and we've written it in a way where we've isolated the cosine pieces and the sine pieces. Okay. So if we want to relate this back to our original, Fourier series in terms of cosine and sine, right? The question is, well, what do these coefficients become? Okay. Well, if we want to relate it back to, right, the real piece, the coefficient for cosine, we called a sub n. So we want to set a sub n to be this thing right here. What about b sub n? Well, b sub n is a coefficient of sine. So we want to set b sub n to be that thing. Okay. Cool. So here we've expressed a sub n and b sub n in terms of these complex exponentials, right? So maybe you can interpret what all we did here is we are given the series, what must a sub n and b sub n be so that we have kind of a Fourier series from before. So we're expressing a sub n, b sub n in terms of c sub n, c sub minus n. Now the question is, right, can we express c sub n in terms of a sub n and b sub n? Okay. So the thinking here is, well, maybe we're given the real Fourier series in terms of cosine and sine. Can we express that same thing in terms of these complex exponentials? So the answer is yes. Before we get there, though, I want to point out a few properties. So in the real case, let me scroll back up here. Right. So in the real case, kind of for these a sub n, right, the index that we're plugging in for n is only ever going to be positive, right? A sub 1, a sub 2, a sub 3, etc. Okay. So in this context, we never consider a sub, say, -1 or a sub -2. Okay? Whereas in the complex case, we do consider c sub -1, c sub -2, etc. Okay? So our question is, right, if we've related a sub n to c sub n, kind of what happens if we plug in -n here? So if you plug in -n, well, recall that already here. So a sub n, this was c sub n plus c sub minus n. So plug in -n here and here. You're going to get -n up there, minus -n over there. Clear the signs. You're going to notice it's exactly a sub n. Okay. So we've shown that these coefficients for cosine, right, kind of just as cosine is symmetric, the coefficients for cosine, they're also going to be symmetric for n and -n. Okay. What happens with b sub n? Okay. So we notice that the coefficients for cosine, right, kind of were even, they're symmetric with respect to n and -n. Right. So for b sub n, well, those are the coefficients for sine, right? Sine of negative whatever is going to be negative sine of whatever. So maybe we expect that b sub -n, whatever this object is, should be minus b sub n. Okay. And this is the case. How does this go? Well, recall that b sub n, this was I times minus c sub n plus c sub minus n. Okay. Or if you want to rewrite this so that the signs are a little more pleasing for the eyes, something like that. Good. Okay. So if we plug in -n here and here, we're going to end up with a -n here and a minus -n there. Clearing the signs, we're going to get that. Okay. So this thing right here almost looks like minus c sub n plus c sub minus n. It's just the signs are flipped. So let's go ahead and pull a minus sign out. Kind of that'll become a minus sign to get this expression, right? Minus I times that, okay? But this whole thing right here, this is exactly that. And so we've shown that b sub minus n is equal to minus b sub n. Okay. So we have these nice little identities for a sub n and b sub n, kind of following from properties that c sub n has, sort of. Cool. So what does that get us? Well, summarizing, so this is how we wrote a sub n and b sub n, right? Coming from way back up here, from what we wanted to set these things. Okay. So what we're going to do now is essentially solve this linear system for C sub n and C sub minus n in terms of an and bn. Okay, so we're going to do, these two lines are just this copied. Okay, here, what we've done is taken this and multiplied it by minus I. So it's going to give minus I b sub n times minus I squared over there. Minus I squared, that's minus -1, which is 1. Okay, so that's what we get down there. Okay. Likewise, if we just multiply this by I, right, I b sub n, I squared over there, I squared is -1. So we're going to get a -1 right there, distribute that. I times b sub n is going to be C sub n minus C sub minus n. Okay, so using these two, right, what we're going to do, add these together, add these together. So when we add these are going to cancel, and we're going to be left with twice C sub minus n. Likewise down here, so add these together, these are going to cancel, and we're going to be left with twice C sub n. Okay, so then what we might say is, well, C sub minus n, this is going to be A sub n minus I b sub n, 2. C sub n is equal to A sub n plus I b sub n, 2. Okay, but one thing to notice is, right, well, A sub n is equal to A sub minus n, but B sub n is equal to minus B sub minus n. So the C sub minus n, this we can write as A sub n plus I, right, minus B sub n over 2, which is going to be A sub n, what did I do here? Plus I b sub minus n over 2. Right, yeah, okay. So that's messing with this b sub n. But then A sub n is equal to A sub minus n. So we can just substitute a minus n there and not change the value of A sub n. So this is going to be A sub minus n plus I b sub minus n over 2. Okay. Actually, let me keep it on the page. Okay, so we've written these things in such a way so that, right, well, C0, that's just A sub 0. Okay, nothing much going on there. But we've written things in a way so that we can write C sub n as just A sub n plus I b sub n over 2. Okay, where this holds for n equals 1, -1, 2, -2, etc. Okay, so we've kind of gotten the behavior for positive and negative n all in one nice little formula. Okay. So with all this in mind, right, well, the sum of C sub n e to the minus I n pi over Lx comes A sub 0, some of that plus some of that, where these C sub n kind of are defined in terms of A sub n and B sub n. Okay, so we've got in this kind of one-to-one correspondence between the complex form and the real form. Okay, so given A sub n and B sub n, we can get C sub n. Given C sub n, we can get A sub n and B sub n. Okay, so we can go back and forth. So these two representations they give the exact same object, right? It's just two ways of writing the same thing. Cool. Okay. Okay, so one more way of rewriting things as well. Suppose n is non-zero, right? So ignore that special coefficient. We had, right, c sub n is that, okay? So we're going to have 1/2 a sub n plus I b sub n. Okay. So we're going to do, right, keep the 1/2 out there. But now the question is, right, well, these we got from the function, right, in cosine. So a sub n and b sub n, these were defined in terms of integrals, remember? So what we can do is just plug in the integrals for each of these pieces, okay? So plugging in the integral for a sub n, we're going to get that. Okay? This is kind of how we computed a sub n using orthogonality of sine, et cetera, or of cosine, et cetera. And then we add in I times kind of b sub n, which is I times this integral for b sub n. And we're going to end up with this thing. So what next? Well, this integral and this integral are over the same bounds. Okay. We can pull out a 1/L. And then within these integrals, we can pull out this f of x. Okay. So we're going to get something like this. Okay. So, right, pull out this L, that's going to get that L there. We're going to have f of x of that plus I f of x of that. Pull out the f of x. We're just left with cosine plus I sine. So another way of expressing this coefficient c sub n is in terms of kind of this integral here. Yeah, right. So very similar to what we had before with the cosine and sine kind of integrals and getting these coefficients. Now we're getting the same coefficients just in terms of these kind of complex, right, exponential integrals. But what we saw before is, well, if we compute these integrals, right, and we get what these c sub n are, we can recover the original a sub n and b sub n. Okay, so again, it's just same object, different representation. Okay, so before going on, so one thing I'll comment, I kind of commented this at the start, but then I realized should not have written things in this way. Okay, right, so I specifically commented here, we're taking the sum over minus, okay? My apologies, this should have been a plus. All of the identities are still the same, okay? This a sub n, whatever, kind of this representation is still going to be the same. The only thing that's going to change is this next, where was it? Here. So the only thing that's going to change is here, instead of having a positive sign there, there's going to be a negative sign, okay? And that notation will come up here in a second when we talk about orthogonality. But yeah, the kind of the formulas and the identities are the same. Derivation, you can modify slightly, go through the same steps with different signs. We'll get the same thing. It's just where it matters is this, you're going to have a minus sign there. Okay. But yeah. No, but the book does it. Actually, I double take it back. We're meant to have the minus sign here. Where was it? The book wants to have the minus sign here. But the book also uses a very non-standard notation for this stuff. Okay. My derivation as written follows the book. So if you're reading along in the book, this is what the book does. If you're doing things in practice and kind of speaking the same language as the majority of mathematicians and probably engineers that use this stuff, this sign should be flipped. It should be a positive. If it matters, I will be explicit and clear about what to do. But point is, book uses non-standard notation. So something to keep in mind. Okay. All that said, this notation doesn't really matter for what we're going to do, kind of talk about next, and that's this notion of orthogonality. Okay. So one way that we got, right, a sub n and b sub, well, the way that we got a sub n and b sub n, right, was we kind of wrote out that Fourier series multiplied by, say, sine of x, or n pi over L x on both sides, integrate over the bounds. Orthogonality relations mean that things cancel, and then you can solve for the b sub n. Okay. All of that hinged on the identity, say, integral from minus L to L of cosine n pi over L x, sine of n pi over L x. Actually, here, I'll just do the sine version because this is really what's happening here. So I'll say this is m pi over Lx, n pi over Lx. This was equal to 0 if n and m were different. Otherwise, this was, so for these bounds, minus L to L, this is equal to just L for n equal to m. Okay. Kind of, this was a trig identity, but these were what we were calling these orthogonality relations, and these let, you know, all of these coefficients sort of cancel and fall away. So we have a similar version for these complex exponentials. Okay. But the thing to keep in mind is, right now we're kind of, right, talking about orthogonality with complex objects. So the inner product that we used for functions right before was the integral, say, over the bounds of f of x times g of x integrated over the interval. Okay, and that worked well for real valued functions. Turns out, as written, it's not going to work for complex valued functions. Okay. And part of that is that we want, so one thing that we want is if you take the inner product of f with itself, this we want to be, let's say, a non-negative real number. Okay, just because we use this object as a notion of length, sort of. Okay. So if we just plug in two complex functions here, right, or take a complex function f and just evaluate this thing, a priori it's not going to be a real number. Okay, let alone positive. Or I should have said that around. It's not going to be positive, let alone real. So in the complex case, we have a different inner product or dot product or whatever you want to call it that we'll use. It's going to take into account the fact that we have a complex valued function. Okay, so the inner product that we're going to use is, well, if we have a function f and a function g, what we're going to do is we're going to integrate them over the domain of interest. But then what we're going to do is multiply the complex conjugate of f with g. Okay, where for a complex number, right, this notation, complex conjugate, just means kind of the real parts are untouched. Anytime you have I, or right, square root of -1, that gets sent to minus I. Right, so Complex conjugate of that is that. Okay. So then the question is, well, what is the inner product of e to the I n pi over L times x with e to the I m pi over L times x? We'll also plug things in. This is what we get. Okay. So now the question is, well, what is this thing? So, well, e to the I theta is equal to cosine of theta plus I sine of theta. So take the complex conjugate of that. What's going to change? This is real, so it's not going to change. Sine right here is real, so not going to change. So what we end up with here is this becomes minus I sine theta. Okay, okay, but minus sine theta is equal to sine of minus theta. So this whole thing is going to be cosine of theta plus I sine of minus theta, which is equal to cosine of minus theta plus I sine of minus theta, right? Because cosine of minus theta is equal to cosine of theta. Well, but this expression is familiar, right? This is just e to the minus I theta. So this tells us that the complex conjugate of e to the I theta is e to the I minus theta, or e to the minus I theta. Okay. So going back to this integral, right, making that conversion here, keeping everything else the same, we're going to end up with this. Multiply two complex exponentials together, you're going to get just the sum of their arguments. Okay. And so here what we've done is we've pulled out this common I, we've pulled out the common pi over Lx, and we've just combined, right, minus n plus n. Cool. So now what we're going to do is kind of break this up into two cases, right? Either n is equal to m, and we have the same function, or n is different to m. What we'd expect or kind of like to say is, well, when n is equal to m, and we have the same function, we're going to get some real positive number, right? Kind of the length or the size of this function. We would also like that when n and m are different, this thing is equal to 0. Okay, and this is going to be the orthogonality relation for complex exponentials. Okay, so if n is equal to m, right, that thing right there becomes 0. So we get e to the 0 pi over Lx, which is e to the 0, which is equal to 1. And so, right, integrate 1 between minus L and L, and that's going to give us 2L. Right? And again, this was exactly the inner product of e to the n pi over Lx with e to the n, e to the I n pi over Lx. Okay. Okay. So if n and m are different, but are both integers, one thing to note is, well, if we take kind of e to the I k pi, where k is an integer, the question is, what is this equal to? Okay. So when k is even, it's going to be 1. When k is odd, it's going to be -1. How do we see this? Well, I guess there are a few ways you could plug in. So maybe so one way to see this might be, right, just explicitly write out cosine k pi plus I sine k pi. This thing is always going to be 0 because sine of k pi is 0. So that's going to be cosine of k pi. And so then here, what we can do is just kind of graph it. So that's 2 pi, pi. So depending on whether or not pi is even or odd, we're going to get either +1 or -1. Another way to see this is to say, well, kind of in the complex plane, where do these points lie, right? So e to the I theta, so this is e to the 0, e to the I pi over 2. Over here is e to the I pi, which is -1. And down here is e to the I 3 pi over 2. Okay. And then once you get to e to the I 2 pi, kind of these functions are periodic, so you get back to e to the 0, which is 1. So either way you want to kind of see it and interpret it is fine, but the point is that we have this identity, right? E to the integer pi is either going to be 1 or -1, depending on whether k is even or odd. Okay, so let's go back to the integral. So this thing right here, right? Well, this is e to a constant times x. So we can integrate it. What do we get? Exactly this thing, which I believe was written before. And you can double check that this is correct, because if you take the derivative of this, this is not quite correct because this is missing an I. But if you take the derivative of this thing is going to come down and it's going to cancel with that, and you're left with, okay. But anyways, so integrate this, we end up with this, evaluate it to bounds. Okay. So pull this thing out, we're going to end up with that along with the I in front that was missing. As well as kind of the actual function evaluated at the two endpoints. Okay, so plug in L for x. With signs, we get exactly this expression. Okay. And so now the question is, well, what is this expression? Here is where we go back to whether or not NM, well, actually, this difference, m minus n, whether or not this is even or odd. Okay. So if n, or if minus n plus m is even, right, this is going to be an even number. Minus this is going to be an even number. So this is even, or the e to the even whatever. So both of those things are going to be equal to 1. So here we're going to end up with, some constant in front times 1 minus 1, which of course is equal to 0. On the other hand, if minus n plus m is odd, right, we're going to have e to the I times an odd number times pi. And what we saw up here was, well, that's equal to -1. Okay. But if this is odd, then minus this is odd. So we end up with L over whatever, constant in front times -1 minus -1, which of course is 0. Okay. So the conclusion is that, well, these two functions are orthogonal, right? If n and m are different, their inner product is 0. Okay. So if we go back to this representation here, right, if we want to, so if we start with this representation and we want to figure out, well, what are these c sub n? What are these constants? Right, we can use the same strategy we did before, where we multiply by sign, integrate over the bounds, things cancel and fall out, whatever. So we're going to replicate that, right? So f of x on the left-hand side, we're going to multiply by e to the I m pi over L x. Same thing on the right-hand side. So this multiplied, and then, so technically it's out here, and then distribute it across this infinite sum, which we're saying we're allowed to do. Okay, now we're going to integrate. Integrate from negative L to L, so it's just sum integral over here, sure. On the other side, sum integral over here, sure. This is a constant, so we can pull it out. This integral here is either going to be 0 if n and m are different, right? And again, we're summing over all possible n. Or it's going to be equal to, what was the constant? 2L, right? When n and m are the same. Okay, so left-hand side is unchanged. The right-hand side is going to simplify down to this expression, right? So here we're saying these integrals are 0 if n and m are different. So these just kind of hone in on the mth term, right? C sub m. Left-hand side is still unchanged. Right-hand side becomes C sub n times 2L. Okay. Rearranging things, we get C sub n is equal to this whole thing right here, which is what we had before. Cool. So just a few different ways of kind of looking at, working with, interpreting these complex exponentials, and really just trying to connect them to kind of the real Fourier series that we worked with previously.